Welcome everyone. It's wonderful to see participants from all around the world joining us today. Here in Sri Lanka, it's afternoon and overcast day in Colombo. Uh, a perfect weather for today's discussion. And we have some housekeeping. The webinar recording will be sent to all participants after this session. And feel free to submit your questions in the Q&A box, and we will address them during the Q&A segment at the end. I'll introduce myself. I'm Prasadini Wickramasinghe, the coordinator for the Greensat Centre of Excellence for Hydrogen in Sri Lanka. It's truly a pleasure to have each of you here for our webinar on enhancing hydrogen safety through consequences and risk modeling software tools. To provide a bit of background, at our Center of Excellence, we are dedicated to advancing hydrogen research and promoting best safety practices with the vision that extends beyond Sri Lanka to the global hydrogen community. Our mission is to build a local expertise, foster international collaboration, and contribute to the safer and more sustainable hydrogen value chain. We are grateful to the National Science Foundation and the Science and Technology Management Information System for their support and recognition. Now, it's my privilege to introduce our esteemed speaker, Sonia Pérez, Effects and Risk Curves Product Manager for Gexcon. Sonia brings over a decade of expertise in process safety and chemical engineering to her role, where she leads the development of tools that assess the consequences of accidental chemical releases, a crucial aspect of ensuring industrial safety. Her insights today will be invaluable. Thank you once again for joining today. Sonia, the floor is yours.
Thank you very much, Prasadini. Thank you for the introduction. And thank you everyone for joining us today, and welcome to our webinar on enhancing hydrogen safety through consequence and risk modeling tools. As hydrogen becomes more prominent as a clean and sustainable energy source, understanding its unique safety challenges is very important. Today, we will explore these challenges and discuss how consequence and risk modeling can play a crucial role in ensuring safe hydrogen operations. During this session, I will also introduce you to the software tools, effects, and risk curves, and demonstrate how they can support hydrogen safety through precise hazard and risk analysis. So if we take a look at our agenda for today's session, I will start with providing a brief overview of Gexcon and explain a little bit about how our solutions align with safety needs. Next, I will cover some key aspects of hydrogen and the inherent safety considerations of handling and storing it. I will then move into the fundamentals of ensuring process safety, and from there, I will introduce effects and risk curves, two software tools for consequence and risk modeling, showing how these tools can support with hazard analysis in hydrogen projects. I'll also share some use cases where these tools can be used effectively for hydrogen safety, along with additional modeling capabilities across different energy sectors. Finally, we will wrap up with a Q&A session later today, so please feel free to add any questions in the Q&A box in the chat as I go through the presentation, and I'll make sure to answer as many questions as possible by the end of the presentation. To begin, let me give you an introduction to Gexcon. We are a leading global provider of safety and risk management solutions, specializing in process safety with a focus on dispersion, fire, and explosion modeling. Our expertise and advanced modeling tools help organizations address complex safety challenges across various high-risk industries, ensuring safer operations in sectors such as hydrogen, ammonia, oil and gas, chemicals, battery manufacturing, nuclear, and many more. We assist our clients in identifying, preventing, and mitigating toxic and flammable hazards in their facilities through different business units. First, we have integral and CFD software modeling tools for consequence and risk modeling studies. And these software tools enable our clients to conduct safety assessments ranging from quick calculations to complex analysis. We also offer expert consulting services, which are backed by over 50 years of research and development experience in major hazard areas. We also perform incident investigation and litigation support, fire and explosion testing services, and we also offer specialized software and process safety training courses. Gexcon is headquartered in Norway, but with a truly global presence. Our offices span multiple regions, including the United States, UK, Netherlands, France, India, Australia, China, and Indonesia, among many others. And we also have a few partners and agents in other locations across the world. This global reach allows us to deliver expert solutions worldwide, while also tailoring our approach to meet specific local needs, regulations, and safety challenges. So with that introduction, let's move on to hydrogen itself, its role in the energy landscape, and why it's becoming a focus for safety modeling. The energy transition is a global shift aimed at moving away from fossil-based sources to zero-carbon alternatives, with the goal of reaching this transformation by 2050. The primary aim of this shift is to reduce carbon dioxide emissions significantly, helping to keep global warming well below 2 degrees Celsius compared to pre-industrial levels. This transition, as you know, is very critical for addressing climate change and building a more sustainable energy future. Hydrogen has emerged as a promising energy carrier due to its potential to address different energy and environmental challenges, such as offering a pathway for decarbonizing sectors that are challenging to electrify, such as heavy industry, aviation, and long-haul transportation. Hydrogen has the highest energy density of any fuel by mass, making it very efficient, especially for applications where space is limited, like fuel cell vehicles. Hydrogen is also a clean fuel, as its main byproduct is water, making it environmentally friendly. Moreover, it can be produced through various methods, including electrolysis using renewable energy sources like wind and solar power. Its versatility spans multiple sectors, from transportation and power generation to industrial processes and energy storage. And it can also be used as an energy storage medium, as a fuel and an industrial raw material, enhancing its potential to support a low-carbon future. While hydrogen is often discussed as a new energy solution, it's actually been used for decades, particularly in industries like petroleum refining, chemical manufacturing, and aerospace, where it powers fuel cells in rocket propulsion. What's changing now is that hydrogen applications are moving beyond industrial use to include fuel cell vehicles, renewable energy storage, and power generation. So with these new applications, we are seeing hydrogen move closer to the public and domestic settings, which brings new safety challenges. To support safe hydrogen deployment, we need to base new designs on a solid understanding of hydrogens and chemical and physical properties, as this approach will be critical to developing safe hydrogen systems for broader use. Hydrogen, while promising, presents unique safety challenges, which are very important for us to understand in order to ensure safe processes. First of all, hydrogen is a highly buoyant molecule, and it typically rises quickly when released, yet in its very cold liquid form, it can behave like a dense gas. Liquefying hydrogen requires extreme low temperatures, close to absolute zero, adding complexity to its storage and transport. Chemically, hydrogen is highly reactive with a wide flammability range, meaning it can ignite over a broad concentration range when mixed with air. Its laminar burning velocity is around 8 times faster than most hydrocarbons, which increases the likelihood of detonation under certain conditions. It ignites easily due to low ignition energy and can even auto-ignite under high-pressure leaks. Additionally, hydrogen flames are nearly invisible in daylight and emit very low thermal radiation, making detection a challenge. And another critical aspect is hydrogen's potential to cause material embrittlement, which requires careful selection of materials for storage and transport to avoid structural failures. In summary, while hydrogen's properties create specific challenges, this can be managed effectively through robust leak detection, proper ventilation, and strict adherence to engineering standards. So understanding these properties is very important to ensure hydrogen safety. At the end, the key takeaway here is that hydrogen is not more dangerous than other fuels, it's just different. So when we account for these differences in design and operations, hydrogen can be used safely, supporting its role in the energy transition. We just need to be aware and understand of the different chemical and physical properties and how to ensure that it's safely used within operations. So how can we analyze the hazards associated with hydrogen to ensure safe operations? Let's look at how process safety principles apply here. Industrial disasters often stem from hazardous releases, system failures, or human error. History has shown us the impact of fires, explosions, and toxic clouds. Fires can cause significant damage to facilities and harm workers and nearby communities, whereas explosions can destroy infrastructure, potentially leading to fatalities and the release of toxic substances. These toxic clouds can travel over large areas, causing severe health impacts or even fatalities. Understanding the causes behind these incidents is essential to prevent future accidents and protect both people and assets. To prevent these scenarios, it's crucial to understand the mechanisms behind hazardous events, all of which begin with a loss of containment. Event risk can help us analyze potential outcomes based on factors like what's the type of the release? Is it instantaneous or semi-continuous? Which is equivalent to, do we have a catastrophic rupture and the release of the entire contents of the vessel, or do we have a leak through a hole in a pipeline, for example? So that's one of the points to consider. The second one is the chemical state. So do we have a liquid, a gas, or a pressurized liquefied gas? Because this state will determine the different phenomena that can occur. And the third one is ignition. Does it occur immediately? Is there an ignition source right at the nozzle where the leak occurs, leading to direct ignition of a flammable cloud, for example, or are ignition sources encountered later on downwind, or is there no ignition sources at all and the flammable cloud doesn't ignite? These factors are foundational in analyzing risks and planning appropriate safety measures. Consequence modeling is key to predicting the outcomes of accidental releases, guiding the design of safer facilities. So by simulating potential incidents, we can design safety measures to prevent accidents, or if they occur, to limit their impact. And this proactive approach helps us avoid worst case outcomes through informed planning. At the end, the type of questions that we want to answer with consequence modeling is, for instance, what's the extent of this jet fire? Will it reach this vulnerable area? There's a school, an urban area, a hospital. Are all these vulnerable areas exposed to potential fires or explosions? So this is the type of information that we would gather from a consequence modeling study. Risk analysis, on the other hand, provides a structured approach to identifying, assessing, and managing risks associated with hazardous events. It involves 5 essential steps. The first step being risk identification, which consists of identifying hazards specific to chemical spills, leaks, explosions, fires, and toxic releases. So what are the potential hazards that can occur within a facility that is handling, storing, or transporting hazardous materials? The second step is a risk assessment, and this one is performed to evaluate the likelihood and impact of these hazards using either qualitative methods like expert judgment or quantitative methods such as using data from past incidents and simulation tools to assess what's the extent of these different events. Third, we have risk prioritization, which consists of ranking risks by severity and likelihood, helping us focus on the most critical issues. Risk mitigation consists of developing strategies and actions to reduce or control risks, which may involve prevention, mitigation, risk transfer such as insurance, or acceptance. And finally, we need to continuously monitor and review risks, and this is crucial to ensure mitigation efforts are effective and make adjustments as needed. Risk modeling is a key component of quantitative risk assessments, what we know as QRAs, which follows consequence modeling to quantify risk. So in step number 1, we have consequence modeling, which focuses on assessing the potential consequences of an accidental release. And in step number 2, risk modeling, it involves quantifying risk using factors like failure frequencies, weather conditions, and population distribution to determine if risks meet regulatory safety standards. So risk modeling is the exercise that we do in order to quantify risk so that we can say, based on data, whether the risk of a facility is acceptable or non-acceptable, so that we can implement prevention or mitigation measures for this risk to be considered acceptable for the people around it. So why do we simulate hydrogen consequences? Conducting consequence analysis for hydrogen operations is crucial for several reasons. First, it enables the safe and optimized design of hydrogen facilities by helping determine appropriate safety distances, for example. It also supports safe operations by modeling worst-case scenarios. To understand potential impacts of hydrogen releases, which could otherwise result in injuries, fatalities, or asset damage. It can also reduce CAPEX and OPEX by preventing over-design of safety systems. It helps evaluate the impact of adding or modifying equipment in hydrogen facilities, ensuring safe expansion. And lastly, it also helps meet industry standards and regulatory compliance by providing a structured approach to safety. So by understanding the potential impacts of hydrogen releases, we can design facilities that protect people, assets, and the environment while supporting the growth of hydrogen as a safe energy source. Effects and risk curves are advanced integral modeling tools that streamline the process of hazard and risk analysis. They both allow us to assess the potential consequences and risks of hazardous material releases efficiently and accurately. To give you a little bit of an introduction to these software tools, effects and risk curves are Gexcon's flagship tools for consequence and risk modeling. They are based on decades of extensive research and are widely used by our clients around the world for safety studies. EFFECTS is an advanced yet user-friendly tool for consequence modeling, and it analyzes the effects of accidental releases of hazardous chemicals, including heat radiation from fires, overpressure levels from explosions, toxic concentrations and doses from dispersion events, and it also translates these physical effects into damage for humans and infrastructure. Risk curves complements this by offering a comprehensive suite for quantitative risk assessments, or what we call QRAs. Risk curves provides results in a variety of formats, including location-specific individual risk contours, AirPath for on-site risk, evaluating the risk at which employees are exposed in an industrial facility, event curves for societal risk, or even societal risk maps for geographical risk representation. And we also have risk ranking reports to support the decision-making process. So risk curves would typically be used to support decisions on urban development, like can I build a certain population in a certain area nearby an industrial facility, or also risk reduction. What are the measures that I can implement to reduce risk, and where is the most effective location for those risk reduction measures? One key advantage is that consequence models in effects are integrated within risk curves, and this allows for seamless quantitative risk assessments by streamlining consequence and risk modeling into one efficient workflow. To tell you a little bit about the history of effects and risk curves, these tools were initially developed in the 80s at TNO. For those who don't know TNO, this is the Dutch research organization for applied scientific research. And it was originally based on the colored books, which were, and still are, a set of guidelines established by the Dutch government in collaboration with TNO. And it was the very first piece of literature for defining like models to simulate fires and explosions, and also including a set of guidelines on how to perform a QRA. So effects and risk curves are or were based on these colored books, and over the years, effects and risk curves have obviously undergone significant enhancements to meet evolving market needs. For example, we've recently introduced a model for analyzing thermal runaway in battery energy storage systems, addressing a critical risk in today's energy landscape. But the user interface has also been improved a lot since the 80s when it first become commercially available. And models are continuously improved, and new models are developed as the market requires for the simulation of different scenarios. So effects and risk curves were originally developed at TNO, but they were acquired by Gexcon in 2018. And these tools have continued to evolve to support a wide range of industries, including chemical, oil and gas, energy transition, hydrogen, batteries, aerospace, etc. Today, effects and risk curves are integral parts of what we call the Gexcon X Suite, which offers both integral and CFD-based solutions designed to revolutionize safety and risk management in high-hazard industries. The X Suite consists of effects and risk curves, integral modeling tools, and flags, which is Gexcon's CFD tool. CFD stands for Computational Fluid Dynamics, offering multiple possibilities for integration. And the main difference between effects and risk curves and FLAGS is that FLAGS as a CFD tool is capable of taking into account complex 3D geometries, accounting for how the fluidodynamics are influenced by interacting surrounding geometries. So it's the X-Suite accessibility that makes it easier for engineers and safety professionals to assess and manage risk associated with various energy transition technologies. To provide some historical context, the need for risk criteria became evident in the 70s when catastrophic chemical industry accidents underscored the importance of public safety around industrial sites. This led to the Seveso guidelines, which mandated companies to perform QRAs or quantitative risk assessments to prevent similar disasters. The guidelines required companies to create safety reports demonstrating compliance with stringent safety standards. And this era also saw the publication of the colored books, which I mentioned before, which provided the first comprehensive guidelines for performing consequence analysis and QRAs. Today, risk criteria are central to urban development planning in many countries across the world, ensuring that industries and communities can coexist safely, even in densely populated areas. Now that we've covered the fundamentals of hydrogen properties and safety considerations, let's look at some practical hydrogen modeling use cases using EFFECTS, from evaluating dispersion and reactivity to simulating potential fire and explosion events. Effects and risk curves offer a robust set of models designed to simulate a vast range of phenomena relevant to different industries and scenarios. These include pool evaporation from liquid spills on ground or water surfaces, detonation scenarios for solid materials, levee fireballs, which can be critical in hydrogen storage scenarios, pool fires, and jet fires for studying various release and ignition conditions, vaporization from liquid cascades, such as overfilled petrol tanks, thermal runaway effects for battery storage systems, relevant as these systems integrate with hydrogen technologies, vessel rupture scenarios, plume rise from warehouse fires or from stacks, and buried pipeline ruptures and crater formation, among many others. So this wide array of capabilities ensures that we are well equipped to model complex interactions and hazards, not just for hydrogen, but across the full spectrum of hazardous materials as well. So how can effects and risk curves support hydrogen safety? As presented earlier today, hydrogen is highly flammable, generally buoyant, and prone to rapid ignition, making it critical to accurately simulate its behavior in various scenarios. So how can effects and risk curves capture these distinct properties? Well, first of all, with effects, we can simulate hydrogen dispersion, whether it behaves as a buoyant, dense, or neutral gas. This flexibility is crucial as hydrogen can exhibit different dispersion behaviors depending on its state. We're talking about hydrogen today, but this is also relevant for other substances that are relevant for the energy transition, such as ammonia. When ammonia is released as a refrigerated gas, so in its liquid state, it will first behave as a dense gas, and then as it warms up to atmospheric conditions, ammonia is lighter than air and it will rise up. So this transition behavior from dense gas to buoyant is also taken into account, as the dispersion model takes into account the entire thermodynamics and physics of that dispersion. Effects can also simulate what we call supersonic releases from high-pressure hydrogen systems, And this is very important because hydrogen is typically stored at pressures around 200, 900 bar, which is very, very high compared to other systems. So being able to accurately simulate these highly pressurized releases, it's very important and currently included in the software modeling capabilities. And this will helps us evaluate storage and transport risks and informs containment strategies as well. Hydrogen's high reactivity and rapid burning rate are also factored into fire and explosion risk assessments, helping us to model potential ignition points and flame spread. With hydrogen's wide probability range, these tools help us understand the increased likelihood of ignition across scenarios, offering insights for both prevention and mitigation measures. We can also factor in hydrogen's low visibility flames, essential for planning emergency response measures where visual detection might be limited. And also, typically, the surface emissive power of hydrogen flames is very low or a lot lower than for hydrocarbons, which is something that we need to keep into account because not only they are potentially non-visible, but the consequences from like exposure to the heat of a hydrogen jet flame is not as severe as with hydrocarbons, for example. We also distinguish between liquid and gaseous hydrogen hazards, such as simulating a BLEBI from liquid hydrogen storage or a hydrogen gas fireball, which is not the same. It doesn't behave the same. So it's important to have two different models for this, because when we have storage of liquefied hydrogen at very low temperatures, there is certain flashing effect with like generation of very cold liquid droplets that vaporize almost instantaneously because of the difference of temperature between the cold hydrogen and the atmosphere. So taking this into account allows us to design targeted safety strategies based on the specific release conditions. Now, let's dive into practical application with a case study on a hydrogen refueling station. In this scenario, we are looking at an accidental release during the transfer of hydrogen from a delivery truck to the station's storage tanks. So imagine that during that unloading process, the dispenser hose at the hydrogen refueling station is accidentally damaged, resulting in a substantial hydrogen gas leak. So through this specific case study, let's see how effects can be applied to model this scenario. So here we're looking at a hydrogen refueling station as it's marked with the blue pin over here and its surrounding environment. So this is the hydrogen refueling station. And over here, we have a regular refueling station that can act as a congestion area. This is very typical because as large volumes of hydrogen might be trapped under the ceiling, this acts as a congestion area, which means that the flammable hydrogen cloud has a very strong potential for explosion, potentially detonation. There's nearby areas like a parking lot and also a residential area, which can become significant concerns. So people in these zones, the parking and the residential area, they could be exposed to the accidental hydrogen release, which highlights the need for thorough safety planning and proper risk mitigation measures in these high traffic areas. So let's look at the different simulation work that we can do here. This is a simulation performed in EFFECTS where we are examining the impact of a hydrogen jet fire at the refueling station. So first of all, we have placed a release of hydrogen at the hydrogen refueling station, which allows us to calculate the outflow of hydrogen and the subsequent hydrogen jet fire, assuming there's an ignition source close to this hydrogen refueling station. This simulation shows the heat radiation contours of the fires and also these surrounding contours which illustrate the extent of the fire's reach regardless of the wind direction. So for this specific case, the wind is blowing from the west, but the surrounding contours show what's the extent of the jet fire, regardless of where is the wind blowing from. So you can see here, the jet fire extends to the refueling station. So we have the hydrogen refueling station and the regular refueling station with petrol or diesel. And this poses a significant risk to the infrastructure of the regular refueling station, especially to the fuel dispensers, the ones with petrol or diesel. If these dispensers are exposed to the heat, a domino effect could result, escalating the hazard even further. So there are different things that we can look at in here. For example, the red contour, this one over here, corresponds to the 35 kilowatt per square meter heat radiation contour, which represents lethal exposure. This means everyone within that area, everyone within this red contour, so everyone in here, is at a higher risk of fatal injury. In a real-world scenario, anyone in this, like within this area, would not survive the exposure to the heat radiation of this jet fire. In this other slide, I am showcasing how the results of this hydrogen jet fire that we just looked at can be seamlessly integrated into Google Earth, which is the image in the right. So by exporting data from EFFECTS, we can create a detailed 3D visualization of the refueling station and its surrounding areas, which provides a much clearer and intuitive view of the potential hazards, making it easier to communicate the risk zones to stakeholders and support decision-making. We can also examine how the outflow angle of a hydrogen release affects the size and intensity of the resulting jet fire. By changing the angle at which hydrogen is released, the fire's size and heat radiation pattern change significantly. So for instance, if we look at these results, higher outflow angles, so if it's released vertically, this causes the jet fire to rise more vertically, which can reduce horizontal impact, but may affect taller areas. Whereas for a lower outflow angle, this results in a wider but more horizontally spread fire, which affects a larger area due to the effect of the wind, which will enhance turbulence. We can also visualize the heat radiation side view, and this visualization is crucial for understanding the extent of damage. For instance, one key application of this visualization is in firewall design. So the heat radiation contours help us identify the critical areas where a firewall should be placed for protecting of infrastructure. We can also use EFFECTS to analyze the potential impact of a hydrogen vapor cloud explosion on the surrounding areas, especially the parking and the residential zones near this hydrogen refueling station. If the hydrogen cloud gets in the way of the regular refueling station, which is marked in red, this will act as a congestion area, which will be responsible for a very strong blast. EFFECTS reports what is the extent of different overpressure levels, such as the 100 millibar contour, which is this one over here. At 100 millibar, windows shatter, and although there will be no fatalities, there will be substantial damage to buildings and vehicles due to the shockwave. At 300 millibar, the damage becomes more severe, which is this darker red contour. Here we have, within this contour, we have total destruction of buildings and lethal body displacement due to the force of the shockwave. You can also use EFFECTS. Let me play this recording again. You can also use effects to explore how the dynamics and the trajectory of a flammable hydrogen cloud can impact the surrounding areas. So you can just see how it develops over time. As you know, hydrogen can be extremely buoyant, so the cloud disperses quickly and rises unless it's constrained. However, as we said, we have a regular refueling station, which is marked in red, that it is acting as a congestion area because it's on the way of the hydrogen flammable cloud, as the ceiling of the hydrogen, as the ceiling of the regular refueling station can trap the cloud, preventing it from rising as it typically would. This creates a dangerous situation where the cloud may remain within the flammable range, LFL to UFL, increasing the likelihood of ignition. Here we see what is the extent of the LFL, which is the lowest concentration at which hydrogen can ignite, which happens to occur right within the dimensions of the regular refueling station. So the LFL contour is the orange one. So if we look at the presentation again, we see how the LFL limits, so the orange shaded contour, what's the extent? So it passes right through and across the regular refueling station. So this dynamic analysis helps us understand which areas will be exposed to a hydrogen's flammable concentrations and enables us to plan for necessary safety measures, such as controlling ignition sources and designing effective venting systems. But now an interesting question, does buoyancy apply to all hydrogen releases? As you can see from this simulation here, this is a side view of a hydrogen flammable cloud for an atmospheric stability class of Pascal B and a wind speed of 3 meters per second. So what we see here is that the plume remains grounded due to the high momentum from the release of hydrogen at 500 bar. So as I said, hydrogen is stored at very high pressures, from 200 to 900 bar. So this very high pressure is the responsible of this plume remaining grounded. As momentum is lost, the cloud rises to around 15 meters, reflecting hydrogen's buoyant properties. So it first stays grounded and then it rises up due to its buoyant behavior. In contrast, under Pascal stability class D, which is neutral atmosphere, with a wind speed of 5 meters per second, the hydrogen cloud remains grounded, completely grounded, which means that attention needs to be paid to ignition sources at ground level, as they will most likely trigger the ignition of this cloud due to the hydrogen's very low ignition energy. So these type of results, this one and this one, are actually consistent with real-world case scenarios where atmospheric stability, wind speed, and release pressure, therefore momentum, all play a crucial role on the dispersion behavior of hydrogen. Using effects for simulating different hydrogen releases can support in concluding that hydrogen clouds are not always buoyant, which reinforces the need for preliminary assessments to determine safe operations and prevent ignition sources from triggering a hazardous cloud ignition at ground level. To provide a little bit of background on the capabilities of the dispersion model in effects, this dispersion model is built based on CFD code, CFD standing for computational fluid dynamics, to describe a one-dimensional plume centerline discretization with functions for lateral and vertical distributions. It ensures conservation of mass, momentum, and energy with additional equations to handle lateral and vertical plume behavior. Since the release of Effects and Risk Curves version 12, which took place in 2022, at the end of 2022, the model can simulate all dispersion phenomena, automatically accounting for transitions between buoyant plumes, dense gas releases, and neutral gases. So the entire thermodynamics of this dispersion process and all of the physics behind the dispersion are taken into account, including phase changes and heat transfer, treating obstacles as integral roughness. And we're talking about hydrogen in particular today, but this is also very important for other substances such as carbon dioxide, which is also very relevant for energy transition initiatives, as we have more and more initiatives on carbon utilization and storage. In these initiatives, if we have a release of carbon dioxide behaves a little bit differently than other chemicals because it suffers from this solid-vapor equilibrium. And therefore, if we have a CO2 jet, it will flash out as a vapor cloud of CO2 with solid, snow particles in there. So the dispersion model will also take into account how for CO2 we have suspended solid snow particles which sublimate, enhancing evaporation and a bigger flammable cloud or potentially toxic cloud. So all of this behavior is taken into account, and same as I mentioned before for ammonia, which when it's released refrigerated, it first behaves as a dense gas and then it behaves as a buoyant plume. All those transitional behaviors are taken into account in the dispersion modeling. Also, concentration distributions are available across the full spatial domain, and the model operates efficiently within seconds. What we see in this slide over here, this visualization of this hydrogen cloud is actually not within EFFECTS at the moment, but we have the capability of extracting data and do some post-processing to get this type of 3D results in other platforms, like Flag CFD post-processor, for example. So that means that potentially in the future, we could see 3D results in EFFECTS as well, because the data is there. We have all the information for vertical and horizontal concentration distributions from a side view or a top view. The dispersion model has undergone extensive validation to ensure accuracy across a wide range of release scenarios. Multi-phase jets, for example, have been validated using datasets from INRIS, CO2 pipe trans, and cool trans for CO2 in various states. Dense gas dispersion has also been widely validated with the PHEMSA model evaluation protocol and datasets from Jackrabbit 2 for vertical jet releases. Lighter than air and neutral gas jets have also been validated for vertical releases of gases like hydrogen. And crater dispersion validation is supported by experimental data from kosher and CO2 safe arrest projects. So in summary, these validations ensure that the model's versatility, that the model is versatile, providing reliable dispersion modeling across various substances, including CO2 for CCUS or carbon capture, utilization, and storage, hydrogen, ammonia, LPG, and many other substances. As we move towards a safer, more sustainable energy future, effects and risk curves can play a key role in evaluating the safety risk associated with emerging energy technologies. However, their modeling possibilities go beyond supporting safe hydrogen handling, but can also support safe ammonia handling, CCUS facilities, battery energy storage systems, LPG, LNG, petrochemical facilities, oil and gas, and many more. Just to see a few relevant examples, with the latest version of Effects and Risk Curves, which was released in September this year, we now offer a model for simulating thermal runaway events in battery energy storage systems. So this model can calculate the release of toxic gases from battery energy storage systems, offering critical insights into the risks and safety measures required. On the latest version of Effects and Risk Curves, we also included a crater model specifically for simulating buried pipeline rupture, which is critical for understanding the risks associated with CO2 exposure in CCS facilities. This model integrates seamlessly with other models such as jet fire and dispersion for comprehensive risk assessments and effective prevention strategies. And this capability enhances safety evaluations for industries involved in LPG, CCUS, and other high-risk infrastructure. Effects and risk curves also offer the ability to simulate tank pit fires, which is the event that occurs when there's a release of a flammable liquid from a storage tank into a bonded area. The size of the pool fire is limited to the shape of the bond or a dike, but can still pose significant heat radiation exposure hazards. Effects allows this by featuring a pool fire model that allows for polygonal shaped pool fires without the need for external CFD add-ons. So you can just simply draw any shape for the liquid spill in a map to simulate this type of tank pit fire scenarios. So that's what you see over here. Like these 4 tanks are in an enclosed bonded area. There's been a liquid spill occupying the whole bond, and then it ignites, forming a pool fire that it's got the shape of the dike within these tanks are contained. Some more advanced models include a tank overfilling model. So prior to the pan spill incident in 2005, the risk associated with overfilling fuel tanks were not fully understood. So it was initially assumed that the liquid cascade would result in a simple spill, but research revealed that evaporation is significantly enhanced due to the formation of liquid cascades from fine liquid droplets. So we have a dedicated model for tank overfilling scenarios. We also have a model for plume rise from warehouse and pool fires. And these hot smoke plumes rise up into the atmosphere, but their dispersion might be affected by the presence of a temperature inversion layer. So if the plume has enough heat momentum to penetrate the mixing layer, it will move upwards and avoid exposure at ground level. So from this simulation, you see that before extinguishing the fire, we have a very strong plume penetrating this mixing layer height. So there will be no toxic exposure at ground level. That's where people are. However, if the fire, if the fire brigade intervenes and starts extinguishing the fire, this will reduce the heat momentum of the plume, potentially no longer penetrating through the mixing layer height, and instead it acts as a ceiling for toxic gases. So this situation increases the risk of toxic exposure at ground level. So to wrap up today's webinar, let's just highlight some key takeaways from today's session. First of all, it's essential to understand hydrogen's unique properties for accurate risk assessment. EFFECTS is a highly effective consequence modeling tool that allows us to evaluate the potential consequences of hazardous chemical releases and risk curves for risk modeling. Also, having a solid grasp of the different phenomena that can occur and the extent of its potential damage helps safety professionals design facilities within built-in safety measures and develop appropriate prevention and mitigation strategies. And finally, EFFECTS supports safety across a wide range of industries, not just hydrogen. From oil and gas and petrochemicals and other high-hazard industries, EFFECTS and risk curves provide the tools required to ensure safe operations, enhance regulatory compliance, and safeguard both people and assets. Thank you all very much for your attention today. I hope you found this session valuable and gained some useful insights today. With that, we will start the Q&A session. So make sure to put all your questions in the Q&A box. I see there's already a few questions in there, so I'll just check a few and see if we can answer some of them today. Let's see. Okay, there's a question from Terence. Can you do a simulation exercise in effects using hydrogen? Well, perhaps let me very quickly show the example that I based the results on the slides on. So as you remember, we had a use case of a hydrogen refueling station. So that's what we have over here. So we have a hydrogen refueling station. This is a regular like petrol and diesel refueling station. And in order to perform these simulations in effects, the first thing that we would need to do is calculate the amount of hydrogen that gets released through the damaged dispenser hose. And for that, we have different release models. Hydrogen is released as a gas, which is why I have a gas release model over here. And then in effects, you would say, okay, I want to simulate the release of hydrogen, which is stored at 9 degrees and 500 bar. For hydrogen releases, it's important to, well, we recommend the use of an expansion type of being isothermal because the hydrogen suffers from negative Joule-Thomson effect. So it's a way of taking this behavior into account, and the release is through a hole of 10 millimeters. So this gas release model will allow us to obtain the representative release rate. So we have 2 kilograms per second coming out of that dispenser hose of hydrogen. And then you could use a flammable dispersion model to calculate the extent of this cloud. The interesting thing about effects is that you can link models one next to the other. So the results calculated on the outflow model, such as the representative release rate, are then used by the dispersion model. That's why these input parameters are in blue. Blue means it's linked. To calculate the dispersion for a Pascal stability class of P and a wind speed of 3 meters per second. So here in the map, you can see the extent of the cloud based on flammability contours. You can also look at the dynamic concentration, how the cloud develops over time. And these surrounding contours, which is the extent of the flammable dispersion cloud when the wind is blowing from different wind directions. And then, as I mentioned before, the cloud is getting on the way of this regular refueling station, which acts as a congestion area. So we can add a congestion area as a receiver, which you can draw in the map, and then define the expansion type to be 2-dimensional. So with a refueling station, you have the ground and the ceiling of the refueling station, so the cloud can only expand sideways. So that's why the expansion type is 2-dimensional. And then define the typical obstacle diameter and the height of the congested area. So you can link this congestion area to the dispersion model to calculate the strength of the explosion. And if you have an ignition source very close to the hydrogen refueling station, you could also use the results from the gas release model to calculate the jet fire. And again, this jet fire model would use the as input parameters the results of the outflow model to calculate the extent of this jet fire. And because we have this heat radiation grid, you can actually read out values from the map. So for example, inside the flame, the surface emissive power is 70 kilowatt per square meters, whereas at the far end of the jet fire is 1 kilowatt per square meter. So this is just a very quick example of all the different phenomena that you can have with hydrogen releases and how it looks like on an effect simulation. Let's see if I can answer one more question, also trying to be sensitive with the time. Let's see. Sachin Patel asks, what are available safety compliance standards one can follow for safe design and testing of liquid hydrogen carrying pipeline? That is a great question, which I can't entirely answer because safety compliance standards differ by country. And this is very common in within process safety. Like every country has its own regulations, requirements, and standards for process safety. And actually, different requirements may depend on who is asking for them. So, for example, in some countries, there's very clear instructions from the government on what are the standards to follow, whereas other countries don't have governmental standards and companies just follow their own criteria for risk assessment. So the answer to that question is it depends on where you're located and it depends on where you're performing your study, because there will be different regulatory requirements depending on the location where you're based. Why do you use 10 millimeters as a hole diameter of release from Pinot Giuseppe? Just because it's a very common diameter size for hydrogen releases, but it is just an example. Like typically you would conduct a sensitivity analysis and perform calculations for multiple hole sizes so that you can get an idea of what are the different consequences using different hole sizes. So it's just an example. You would want to do full bore rupture, smaller hole sizes, bigger hole sizes to make sure that you cover for the entire range of the possible worst case scenarios. Okay, I think that's all we have time for today. Thank you so much for your attention. I'll pass the word to Prasadini now. And if you have any additional questions, please feel free to get in touch with us and we will try to answer to all of the unanswered questions after the webinar as well.
Thank you. Thank you very much, Sonia, for this insightful and informative session. And on behalf of the Greenstat Center of Excellence for Hydrogen in Sri Lanka, I would like to extend our heartfelt gratitude to you for sharing your expertise with us today. Your deep insights into hydrogen safety and the role of consequence and risk modeling have been incredibly valuable, especially as we strive to build a safer and more resilient hydrogen ecosystem. I'd also like to thank all our participants. Your presence here today underscores the importance of collaboration and knowledge sharing as we tackle global challenges together. To everyone who joined us today, we hope this session has provided you with valuable insights and practical tools. As we wrap up, please remember that the recording of this webinar will be sent to all registrants. Once again, thank you, Sonia, and thank you all the participants being a part of this important conversation. We look forward to seeing you at our future events as we continue to work together towards a safer, sustainable hydrogen future. Stay safe and have a wonderful day. Thank you. Bye-bye.
Thank you very much, everyone.